Welcome to Aero 1020, Theory of Flight, presentation number 7 on the continuity principle. In this presentation, we'll discuss the definition of mass, the conservation of mass, and the definition of energy. And we'll talk about the different types of energy and the conservation of energy and how the continuity principle helps us to achieve lift. So what is the definition of mass? Remember that mass is the density of an object. It's not the weight of an object. Weight is different than mass. Mass is the quantity of inertia or resistance to acceleration scientifically. And the more mass that an object has, the more force required to move that mass. You can find force by taking the mass and dividing it by acceleration, the acceleration of gravity. If we use pounds for mass and 32.2 feet per second squared for velocity or gravity, we end up measuring mass in slugs. So think of two identical pillowcases. One is filled with feathers, the other is filled with bricks. Which one is heavier and denser? The pillowcase holding the bricks has more mass. Even though they're both the same size, the bricks are more dense than the feathers. So does air have mass? Well, yes, even though we can't see air, it still has mass. Air is made up of molecules. To better understand the properties of air, we need to look at a couple of different laws. The first law is Boyle's law, which says that the volume of a gas is inversely proportional to the pressure of the gas. So does air have mass? Well, even though we can't see air, air is made up of molecules, and therefore air does have mass. Boyle's law says that the volume of gas is inversely proportional to the pressure of the gas. So if we isolate pressure and volume and keep temperature constant, mathematically speaking, pressure 1 times volume 1 equals pressure 2 times volume 2. And we can use the example of a large glass box of air. It's airtight, reducing the same air to a smaller airtight glass box. Did the mass change? No, the mass stayed the same. That's conservation of mass. Here's an illustration of Boyle's law from NASA. And as you can see in this illustration, as the volume decreases, pressure increases, or as the pressure increases, volume decreases. And that's keeping temperature constant. So this is a sealed container. Notice that the number of molecules never change. So the mass of this gas is the same. It's conservation of mass. That's Boyle's law. As we discussed in the last presentation, Newton's second law states that force equals mass times acceleration. So the greater the mass, the more force is needed to accelerate a body. For example, a large aircraft. So in relation to the conservation of energy, remember mass is conserved, and so is energy. Energy is conserved. Energy cannot be created or destroyed, but it can be changed. You can change energy from usable energy to unusable energy. And there are two different types of usable energy. There's kinetic energy and there's potential energy. Potential energy is possible energy. It is the stored energy, if you will. Kinetic energy is the energy of movement. So potential energy plus kinetic energy equals total energy. And remember, potential energy is mass times gravity times height. Kinetic energy equals 1/2 times mass times velocity squared. So putting these together, mass times gravity times height, or potential energy, plus 1/2 times mass times velocity squared, or kinetic energy, should equal total energy. And the conservation of energy says that the total energy is constant. So if we have energy, can we do work? Remember, work is defined as a force times a distance. So if I can move something, then I'm performing work with energy. So can we do work with a compressed spring? Well, think about a pinball machine. In a pinball machine, you pull back to compress a spring, and then you let go to release the energy in that spring. So when you compress a spring, it's potential energy. You release it, it's kinetic energy. Can we do work with a compressed gas then? The answer is, of course we can. A compressed gas can release energy. And we can add this to the equation for total energy. So mass times gravity times height, or potential energy, plus 1/2 times mass times velocity squared, which is kinetic energy, plus pressure times volume, which is the energy of a compressed gas, equals total energy. So let's just imagine two chunks of air, condition 1, and after the chunk of air has moved, condition 2. We can use the equation for energy to describe the energy in each condition. In other words, mass times gravity times height plus 1/2 mass times velocity squared plus pressure times volume equals total energy. Now the other thing that hasn't changed between the two conditions is volume. And since volume hasn't changed, we can divide both sides by volume to simplify the equation further. And we come up with 1/2 times mass times velocity squared divided by volume plus pressure. Since mass over volume equals density, or rho, now we can replace that with rho in the equation. So we have 1/2 times rho times velocity squared plus pressure. Bernoulli's equation for dynamic pressure is 1/2 times rho times velocity squared. And the conservation of energy says that the total pressure is constant or conserved. So as the speed of a fluid increases, dynamic pressure goes up. Static pressure has to go down as a result of the conservation of energy. Total pressure must remain constant. Before we move on to the study of moving air, or aerodynamics, we should probably discuss the study of still air, or stationary air, called aerostatics. So how does a balloon float in the air? So what are the forces acting on a balloon? Well, for one, the weight of the air is acting on the balloon. And we can signify the weight of the air as weight equals mass times gravity. But when we're talking about a gas like air, we should include volume. So we can multiply that equation by volume over volume, which is basically multiplying it by 1, which will not change the equation. But when we do that, we get weight equals mass times gravity times volume over volume. And we can eliminate one of those volumes by combining mass over volume, which equals density. So now we can further simplify the equation to weight equals density times gravity times volume. So let's just imagine that this square is a balloon for simplicity's sake. And again, weight equals rho, or density times gravity times volume. volume equals h, which is the height of the balloon, times A, which is the area. So if volume equals height times the area, then weight equals density times gravity times height times the area. If pressure 1 below the balloon is greater than pressure 2 above the balloon, and pressure 1 times area minus pressure 2 times area minus the weight of the balloon equals 0, then the balloon will float. So let's solve for rho times gravity times height. Now we can further simplify the equation by dividing both sides by area. And when we do that, we get P1 minus P2 minus rho times gravity times height equals 0. So now we can solve for rho times gravity times height. We do that by adding rho times gravity times height to both sides. And when we do that, we get P1 minus P2 equals rho times gravity times height. This is what is known as a hydrostatic equation. Now the hydrostatic equation includes rho times gravity times height, and it's important to remember that that's a weight or a density term. P1 minus P2 are pressure terms, so that's pressure 1 minus pressure 2. If the balloon is floating, then the left side of the equation has to be equal to the right side of the equation. So the pressure differential should be equal to the weight. So when the weight is equal to the differential pressure, the balloon will float. But how do we get the balloon to rise? We can't change the pressure. We can't change P1 or P2. All we can do is reduce the density to make the pressure differential greater than the weight. And we do that by heating the air. So that's why in a hot air balloon, as we heat the air, the density of the air in the balloon becomes less, and that reduces that side of the equation, allowing the balloon to rise. So balloons are usually very tall because there needs to be a big enough difference between the pressure at the bottom of the balloon and the pressure at the top of the balloon. But how about this plank pictured in this slide? There's not much difference between P1 and P2. And the same is true of an aircraft wing. The weight will always be greater than the pressure differential, so the wing will never float. And that's why airplanes are called heavier than air. So how can we get something that is heavier than air to float? Well, one thing we can do is introduce velocity or moving air. And that's where we get to aerodynamics. Aerodynamics is the study of moving air. So what happens if we introduce velocity or speed over the top and the bottom of the plank? Well, if we can speed up the fluid over the top of the plank, we can reduce the pressure according to Bernoulli's principle. And so we can derive Bernoulli's principle by first subtracting P2 from both sides of this equation. So when we do that, we get P1 minus P2 plus 1/2 rho times velocity squared equals 1/2 times rho velocity squared 2. Then to further simplify, we can subtract 1/2 times rho times velocity squared 1 from both sides. And we get P1 minus P2 equals 1/2 times rho times velocity squared 2 minus velocity squared 1. That is Bernoulli's equation. Looking back to the Wright brothers in the late 1800s, they were actually bicycle mechanics working in Ohio, but they were interested in flight, so they built a contraption called a wind tunnel to study air and motion. And the study of air and motion is the study of aerodynamics. Back then, the speeds that the Wright brothers achieved in their wind tunnel was very limited. Today, wind tunnels are far more impressive, far more complicated, and can achieve wind speeds much higher than they could achieve back in the Wright brothers' time. So what happens in a wind tunnel? Well, a wind tunnel is basically a venturi tube with a very narrow opening. And when you force air through a narrow opening, what happens is the velocity of that air increases. So to illustrate the continuity principle, let's focus on the velocity or the speed of the air and the area in the wind tunnel section. What happens to the velocity when the area is decreased? As I said before, when you force air through a narrow opening, in other words, you decrease the area that the air is flowing through, the velocity will increase. In this illustration, you see a wind tunnel, and on the left side, the velocity is 90 feet per second through an area of 10 inches squared. If we reduce that area to 2 inches squared, what happens to the velocity? So to illustrate the continuity principle, we can just plug in the numbers for velocity and area to find velocity 2. The continuity principle states that velocity 1 times area 1 should equal velocity 2 times area 2. So on the left side of the wind tunnel, we had 90 feet per second, that was velocity 1, times 10 inches squared, and that was area 1. That should equal velocity 2 times 2 inches squared. So when we break the equation down further, we get 900 equals velocity 2 times 2. Divide each side by 2 to solve for velocity 2, and we get velocity 2 equals 450 feet per second. So just by reducing the area that the air is passing through, we've increased the velocity by 500%, just by reducing the area that the air is flowing through by 80%. So how do we create lift? We know that as the velocity of air increases, the pressure decreases. The wind tunnel demonstrates how the velocity is related to area. As area is decreased, velocity increases. But what else changes? Well, Daniel Bernoulli was a scientist who studied the properties of moving fluid. And one of those properties was pressure. Pressure, or air pressure, will change as the velocity changes. Daniel Bernoulli was born in 1700, and he was an Austrian physicist and mathematician that studied in St. Petersburg, Russia. And he studied water in pipes, like plumbing, and what was called fluid dynamics. At slow speeds, water behaves a lot like air. Both behave as fluids. So in Bernoulli's equation, total air pressure is a result of both static pressure and dynamic pressure. Static pressure is the pressure of still air. Dynamic pressure is the pressure of moving air. So when air gains motion, some of that static pressure has to be translated into dynamic pressure. Again, static pressure plus dynamic pressure is a constant. So if one is increased, the other must be decreased. When you are looking at a venturi tube, if the air's velocity is increased at the small section, then the static pressure will be decreased because the dynamic pressure is increased. That's Bernoulli's theorem. So let's take a look at Bernoulli's equation. Remember the mathematical order of operations. When we do this equation, we'll do the parentheses first. So on the right side we have velocity 2 minus velocity 1 in parentheses, so we'll do that first. and that comes out to 202,500 minus 8,100, or 194,400. Then we can multiply the standard density of 0.00238 by 1/2 and multiply that result by 194 to get 231. Now we need to somehow make P2 a positive. It's a negative on the left side, so if we add P2 to both sides, we come up with 2,117 equals 231 plus P2. Now we can solve for P2 by subtracting 231 from each side, which gives us a P2 of 1,886 pounds per square foot. So as you can see, the pressure of 2,117 pounds per square foot has actually gone down because of the velocity increasing to 1,886 pounds per square foot. So lift is defined as the differential pressure, the net differential pressure between the upper and lower surfaces of an airfoil. As you can see in this illustration, the vector arrows represent lift, and as you can see, the arrows at the top of the airfoil are longer than the arrows underneath the airfoil, signifying low pressure and more lift above the airfoil, because the velocity of the air flowing over the airfoil, because of the shape of the airfoil, is higher than the velocity of the air flowing underneath the airfoil. That is what creates lift. In addition to the differential pressure creating lift, we also have downwash being created by the flow of the air over the airfoil. And because of that downward force, we have an equal and opposite reaction upward, which contributes to lift as well. And that's due to Newton's third law: for every action, there's an equal and opposite reaction. Well, that's the end of presentation number 7 on the continuity principle. Next, in presentation 8, we'll go over lift.